All right, welcome to this video on molecular structure. In this video, we're going to be going over how to draw Lewis structures. So there's basically 3 steps that you're going to follow in drawing Lewis structures. The first step is you're going to determine the number of valence electrons. The second step is you're going to determine the central atom. And the third step is if the central atom is in the first 2 periods, you're going to follow the octet rule. So let's go ahead and jump in with some examples. So here we have a tin dichloride. So we're just going to go through the steps. So the first step, we're going to determine the number of valence electrons. Now the number of valence electrons is very simple to figure out because it's simply whatever group number it's in, as long as you're following the A series. So if we look at tin, for example, it's in the 4A series. So tin is going to have 4 valence electrons. Now chlorine, on the other hand, it's in the 7A series. So chlorine is going to have 7 valence electrons. Now we're going to multiply that 7 by 2 because there's 2 chlorines to give us a total of 14. We're going to add them up, and now we have a total of 18 valence electrons. Now from here, what we're going to do is we're going to subtract from this total number of valence electrons, we're going to subtract the highest multiple of 8. In this case, for example, it's 16. 8 times 2 gives 16. So we're going to subtract 16. This will make sense as we move forward in the video. So 18 minus 16 is going to give us 2. Whatever you get here, you're going to divide by 2. So in this case, it's 2. We're going to divide by 2, giving us 1. Now the reason we did this is because whatever you multiply 8 by 8 here, in this case we multiplied by 2, this number is going to be the number of surrounding atoms. Surrounding atoms. So that 2 is surrounding atoms. This one right here, this one is also important because this one is going to tell us how many electron lone pairs we have. So electron lone pairs. So here we're going to have one central atom surrounded by 2 atoms. So we're surrounded by 2 and 1 electron lone pair. So just 1 E. So AX2E. So this is step 1. Step 2, we're going to determine the central atom. Now the central atom is either the atom with the lower group number, smaller group number, or the one that's least electronegative. So if we look at tin, for example, tin is in the 4A group versus chlorine in the 7A group. 4 is obviously lower than 7, so tin is going to be our central atom. Okay, so we have our central atom, the A. We have the central atom. Now we're going to have 2 surrounding atoms. In this case, they're both chlorine. So we're going to have our 2 surrounding atoms, chlorine, and 1 electron lone pair. There's our electron lone pair. From here, we're going to go to step 3. Now step 3, for the central atoms in the first 2 periods, it's going to follow the octet rule. The tin is not in the first 2 periods, so it can break the octet rule. So this is okay for tin. It can break it. Chlorine, on the other hand, is surrounding atoms. The surrounding atom, so the surrounding atoms have to follow the octet rule. So we're just going to fill it out to complete the octet. And there you have it. So this is the Lewis structure for tin dichloride. If you ever want to double check it, you can simply count the total number of valence electrons. Total number of valence electrons has to match. So we'll go ahead and do that to make sure it matches 18. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It matches out. You can also check formal charges, but we won't be checking formal charges in this video. Let's do another example. Alright, so here we have phosphorus hexafluoride anion. Here we have a molecule with a charge. We're going to be doing the same thing. The only difference is we're going to add an electron to the total number of valence electrons. So we're first going to determine the number of electrons. We have phosphorus. Phosphorus is in the 5A group, so it's going to have 5 valence electrons. Fluorine is in the 7A group, so it's going to have 7 valence electrons, but there's 6 of them. So we're going to multiply by 6, giving us a total of 42. We're going to add these up. $47 total valence electrons, but we're going to add one more to account for this negative charge, this extra electron. So we have a total of 48 electrons. Again, from here, we're going to subtract the highest multiple of 8. In this case, it's 48. Eight times 6, 48. So 48 minus 48 is 0. Whatever we get here, we're going to divide by 2. 0 divided by 2, again, is 0. So we're going to have, for this here, we're going to have one central atom surrounded by 6 atoms and 0 electron lone pairs. So we're going to have an AX6 configuration. So step 1. Step 2, determine the central atom. Again, the central atom is going to be the lower group number, or less electronegative. In this case, phosphorus is in the 5A group number, fluorine is in the 7A group number. So phosphorus is going to be our central atom. Okay, we're going to surround it with 6 atoms. So 1, 2, 3, 4, 5, 6. In this case, they're all fluorine. Okay, rule number 3. If the central atom is in the first 2 periods, it follows the octet. Phosphorus is not in the first 2 periods, so it can break the octet. This is fine. Now, fluorine is the outer, the surrounding atom, so that has to follow the octet. So I'm just going to go ahead and fill out the octet for all these fluorines. There we go. Almost done. We just got to account for this negative charge. To do that, you're simply going to put this in brackets and add a negative. And there you have it. This is the Lewis structure for phosphorus hexafluoride anion. All right, let's do one more example. All right, so here we have bromine trifluoride. Same thing. Determine the number of valence electrons. Bromine is in the 7A group number, so it's going to have 7 valence electrons. The fluorine is also in the 7A group number, so it's going to have 7 valence electrons. There's 3 of them, so we're going to multiply, giving us a total of 21. We're going to add them together. 28 total valence electrons. From this 28, we're going to subtract the highest multiple of 8. So we're going to have 24. 8 times 3. 8 times 3, 24. So 28 minus 24 is 4. From this number, we're going to divide by 2, giving us 2. So here we're going to have one central atom with 3 surrounding atoms and 2 electron lone pairs. So AX3E2. So step number 2, determine the central atom. Here in this case, they're both in the same group number, but if we look at the electronegativity, we're going to see that the bromine atom is less electronegative than the fluorine. If they're in the same group, the general trend for electronegativity is the lower they get in the group, the less electronegative they are. So bromine is lower than the fluorine, so it's less electronegative than the fluorine. So bromine is going to be our central atom. So our central atom is going to be surrounded by 3 atoms. In this case, they're all fluorine. And we're going to have 2 electron lone pairs. So 1 pair, 2 pairs. Bromine, it does not fall in the first 2 periods, so it doesn't have to follow the octet. The fluorine, however, is surrounding atoms. The surrounding atoms will follow the octet. So I'm just going to go ahead and fill out the octet for all the fluorines. there you have it. This is the Lewis structure for bromine trifluoride. Again, if you want to double check, just count the total number of valence electrons. We can do that now. We have 2, 4, 6, 8 times 2, 3, 24, 25, 26, 27, 28. That checks out. Again, you could calculate the formal charges as well, but we won't be covering that in this video. And that's it. Just a couple of things I want to point out. If you notice, all the molecules I drew did not have hydrogen. The reason they didn't have hydrogen is because this trick doesn't work for hydrogens. Also, the total number of valence electrons was always an even number. This also doesn't work for radicals. So when you have an odd number of valence electrons, it won't work. So it won't work for radicals. I also only did central atoms singly bonded to the surrounding atoms. It does work for multiple bonds, but it's a little more in depth than what I want to cover here. So just remember that it doesn't work for hydrogens, molecules of hydrogens, or radicals, odd number of valence electrons. And that's going to do it for this first video on molecular structure.